Okay, here's the homework for 2-5. We're on page 140 and we'll start with number 11. In number 11 we've got a function given, f of x equals x cubed plus 9x, and then we're given 3 roots and we need to confirm that those are the roots of the function. So they give us negative 3i, negative 3i, positive 3i, and 0. So if we were to factor out an x, so this is where the 0 root comes from. And then if we do x squared plus 9 equals 0, x squared equals negative 9, square root, and we get x equals plus or minus 3i. So there's other ways to get this root, other ways to solve this problem. You could set up the 3 roots and FOIL them out and see if you get the original function. You could use the quadratic formula. But this is called, what is this called? It really only works when you don't have a middle x term. It's called using a radical to solve a quadratic, but it works for this problem. So we'll look at some other techniques as we move forward. In number 13, we are given a graph and a function, and we are supposed to find all of the zeros of the function. So in number 13, let me write out the function. It's x cubed minus 4x squared plus x minus 4. And then we're given a graph, which I'm not going to sketch, but as I'm looking at it, 1, 2, 3, 4, it looks like we have a 0, or our graph is crossing the x-axis at x equals 4. So I'm going to go ahead and synthetically divide that. Of course, I've done a quick check to make sure I'm in descending order of the variable and I don't need to insert any placeholders. So 1 times 4 is 4, that's 0, 0, 1, 4, 0. So what I'm left with is x squared plus 1. And so this is the thing I need to factor or solve, and I'm going to use that same technique where I use a radical. So x is equal to plus or minus I. Remember that I terms always appear in conjugate pairs. So we had to find all the zeros, so I can list them out. They are 4, I, and negative I. And is there a relationship between the number of real zeros and the number of x-intercepts? Absolutely. It's a 1-to-1 relationship. It's the same. There was 1 intercept and there's 1 real 0. We could have used Descartes' rule of signs to find out how many positive zeros they are. We have 1, 2, 3 sign changes, which means there would either be 3 or 1 real roots, and in this case there was just 1. In number 15, we are given the same thing, a function and a graph. And my graph does not touch at all. So that tells me there are no real zeros. All the zeros are imaginary. So now I'm kind of stuck. I have no way to find the zeros unless I could use the rational root theorem, and I could do all my p's divided by all my q's, and so I could get a list of the potential roots, but I already know none of those would work, because if I look at the sign changes, I have 0 sign changes, so I have 0 positive, 0 negative real roots. So my only hope is that this will factor, and fortunately I can see that it has one of those factoring patterns where it's a perfect square trinomial, perfect square at the beginning, perfect square at the end. The middle term is the square root times 2. So I can actually go ahead and factor this. And my roots are actually, they have multiplicity of 2. And they're plus or minus 2. Is it 2i? Yeah, because if I did x squared plus 2 equals 0, x squared equals negative 2, x equals square root of negative 2. So it's the square root of 2i, or I'm actually used to writing it as plus or minus I radical 2. That way you're never going to confuse and think that that I is up underneath the radical symbol. In number 21, the directions say find all the zeros, write the polynomial as a product of factors, use a graphing utility to verify your results. So in number 21, let me write down the function f of x equals x squared plus 25. So I'm already starting to notice a pattern with those. I get x squared equals square root of negative 25, or rather x equals square root of negative 25. So x equals plus or minus 5i. And I'm supposed to use a graphing utility. So let's take a look. I think I was doing some stat plot stuff last night, so let me, or yesterday's lesson. So let me make sure my plots are off before I try to graph something. And then x squared plus 25, graph it. And let me adjust my window, go back to negative 10, positive 10. Let's see if we can see where this graph is. Okay, there it is, way up high. So I could find the x-intercept by plugging 0 in for x, and so yeah, I needed to be up at 25 to be able to view that. Yeah, okay, so number 23, we've got f of x equals 16x to the 4th minus 81. And we're supposed to find all the roots. And fortunately for me, I notice that that's a difference of squares, so I'm going to go ahead and factor it. I get 4x squared plus 9 and 4x squared minus 9. And then I see this guy is a difference of squares as well, so let me rewrite that. 4x squared plus 9 is not a difference of squares, and I know for a fact that one doesn't factor, so we'll deal with that in a minute. Then 4x squared minus 9 would go to 2x plus 3, 2x minus 3. So I can see this root is negative 3/2, and this one is positive 3/2. 4x squared plus 9, I've got to see what values would make that be 0. So 4x squared equals negative 9, x squared equals negative 9/4. Square root, and we get x equals, that's a perfect square, so that's going to be plus or minus 3/2, and then with the negative in there, that's I. So here's 1, 2, 3, 4 roots. So if I'm going to write this as the product of factors, that's going to be x minus 3/2, x plus 3/2, x minus 3/2 I, x plus 3/2 I. In number 27, we have finally a polynomial that doesn't have one of those patterns. So we have x to the 4th plus 10x squared plus 9, and So we want to look for a root. So let's go ahead and plot this in our graphs. X to the fourth plus 10x squared plus 9. And that way, if I look at the graph, so my graph is up here, it never touches the axes. So since it's a fourth and a squared, it follows the same patterns as factoring a trinomial. So I want two things that multiply to equal 9 that add to equal 10. So that would be 9 and 1. So I'm going to have x squared plus 9 and x squared plus 1. And I know that those patterns are going to give me imaginary roots. So x is going to be plus or minus 3i and plus or minus I. In number 31, I'm going to go to a new page. Alright, so number 31, f of t equals t cubed minus 3t squared minus 15t plus 125. And so I am looking for, I have two sign changes, so there's going to be two real roots. So let's use a graph. Let me zoom back in to change my window. Let me use a graph to figure out what some of those will be. I'll go x to the third minus 3x squared minus 15x plus 125. So you can see how I entered that in. So I can't really see all the zeros, but I think if I just take out 1, then I'll be able to FOIL or factor or quadratic the rest. So that root is at -5, so I'm going to go ahead and synthetically divide that out. So 1 times -5, -5, -8, 40, 25, -125, 0. Okay, so we get t squared minus 8t plus 25. And I can already tell you that there is no value of 25 that when you multiply, no factors that when you multiply them they add up to equal 8. So now I'm just going to use the quadratic formula. So that, if you remember, is negative b plus or minus square root of b squared minus 4ac all over 2a. So I like to list out a, b, and c. A is 1, b is -8, c is positive 25. So now I'm going to plug things in. 8 plus or minus b squared is 64 minus 4 times 25 times a all over 2. So that's 8 plus or minus, now that's 64 minus 100, so that's square root of -36. So see, this is where your imaginary roots come in. So square root of -36 is plus or minus 6i. So I could write that as 8 plus or minus 6i over 2, and then 2 comes out of everything. So that would be 4 plus or minus 3i. And that's actually 2 roots. So I've got those 2 plus my -5. So that's the 3 roots that are required. And let's see, write the solution as a polynomial. So we want to write x minus 5, x minus 4 plus 3i, and x minus 4 minus 3i. So I could simplify those a little bit further. X minus 5, distribute the negative. So we have x minus 4 minus 3i, x minus 4 plus 3i. and that's my solution.